Hello everyone, this is K. Aditya, the coordinator of the Civinar and the moderator for today's session. I welcome you all to our first webinar in the series of webinar called Civinar. Our first webinar is the topic of automation in bridge inspection. I would like to start by giving you all a brief about our institute, that is the National Institute of Technology, Rourkela. National Institute of Technology, Rourkela was founded in 1962 with an aim to advance and spread knowledge in the area of science and technology, leading to creation of wealth and welfare of humanity. With a ranking of 16 in the NIRF engineering criteria, our institute is one of the only institutions in the country to have a world ranking of 650. Now I would like to invite Professor Subhajit Mandal, our faculty advisor of CEST Club and the chief patron of the Civinar, to give you some details about Civinar. Professor Subhajit Mandal, I would
Yeah.
request you to start.
Initially, actually, CEST Club used to organize locally some event. So this year, due to COVID time, no one is able to going outside. So I asked the student, can you arrange a webinar like things so that we can communicate with the world, world organization or research laboratory, some professors, so that we can learn from them. And we also, if we find if there is any option for research collaboration or joint project, guiding all the things. Then Satyadeep was very uh, active member of this club. So he said, yes, sir. Then within a week, we arrange it. I thanks all the members, Satyadeep, Aditya, Subham, for organizing such webinar. So here, the good thing is that staying up abroad for you also is very difficult to come to India and going and giving a lecture on your topic. But now that COVID has learned the teachers that how we can use the technology. I thanks all the member of this that CEST club to organize such beautiful thing. We can have we can exchange our ideas here, and it's a live session. Many people can join, and thereafter also it will stay in the YouTube, so they can also go through it and they can learn many things from this webinar. So I just ask Aditya to start this session here.
Thank you, Professor Subhajit Mandal. I would like to invite Professor Sriram to start with his presentation.
Okay. Good morning, good evening, good afternoon, wherever you are, whichever time zone you are. I hope you're able to see my screen. Let me just make one confirmation. See my screen, and then let me just get started with it. Yeah, okay, good. So it's all confirmed. So let me just start. So I was contacted by your club, I would say about a couple of weeks ago, and I thought, many of the students, especially in India now, right, with all the visa issues, COVID issues, not exams not having happening on time, I would understand a lot of you will be under stress, a lot of uncertainty as to what is going to happen with your lives, with your studies. So I thought, oh, maybe I can spend an hour with all of you on this live web session and sort of. I can't answer obviously all the questions, but I can try and from the perspective of someone who's on the other side now and regularly recruiting students for graduate school. I thought at least I can give you my perspective. I can give you my thoughts on this. But again, I think your club wanted to talk about some technical things. So I initially thought we'll just keep it all interactive, but because this talk has some technical aspects to it, so I'll just spend maybe 10 minutes just talking about what some of the technical stuff, and then I will conclude maybe in about 10 to 12 minutes, and then from there on we can have an interactive session. Feel free to ask me, other than even the technical stuff. Of course, you can ask me questions on the technical presentation or other things that we are doing, but definitely ask me other things about, your career as a civil engineer, like what can you do and how things are going to look in your career in the future, right? So things is civil engineering is evolving. So I will be happy to answer any questions related to your career, your studies, your technical interests, etc. So I'll just talk a little bit about bridge inspections here. So just give you a very high level overview of what it is. Of course, my name is Sriram Narasimhan. I am a professor at the University of Waterloo in Canada. It's one of the largest engineering schools in North America. So for those of you who do not know where Waterloo is right there. You see the black arrow. That is just west of Toronto, so which is about, I would say, hour and a half from Buffalo, New York. So you can see all the big cities in that little map there. You have Cleveland, you have Detroit, you have Buffalo, you have Chicago. These are all Great Lakes, part of big cities on the Great Lakes. So we are sort of in the northeastern part of North America, and Toronto is the largest city in Canada, and Waterloo is about 100 kilometers west of Toronto. Waterloo is sort of home to a lot of technology. For those of you who are still old enough to remember BlackBerry phones were first developed in Waterloo. It was a startup company. Now we have a lot of companies like Myovision. I'm going to show you something. So it's a technology hub. Waterloo is a technology hub. So we have about 41,000 full and part-time students. So it's a pretty large university. But Waterloo is known for its technical engineering and mathematics. It has been in 1957. It's relatively a young university. Waterloo opened with just 74 students, and now we have about 41,000 students. In 2019, we had over 6,000 undergraduate degrees, nearly 2,000 master's degrees, and about 320 or 327 PhD degrees. So we are a pretty significant size in terms of undergraduate and master's and PhD degrees awarded. We have a large and a beautiful campus. We have over 100 buildings with 6 faculties: engineering, mathematics, sciences, and you can look it all up on our website. We are very highly ranked in Canada. We are number 1 innovative university for 28 consecutive years. So when people talk about University of Waterloo, they think about innovation, all the new things. We are also the number 1 comprehensive research university for 12 consecutive years. What this means is we are highly regarded in Canada. In terms of subject rankings, we are number 2 in computer science and number 2 in engineering. I think when people think of Waterloo, at least in Canada, Waterloo is synonymous with what is called co-op program. Our undergraduate engineering and a lot of our undergraduate programs like engineering and mathematics, they are what is called a co-op program. That means what happens is it takes actually 5 years to complete, not 4 years. But then students work, study. So one semester they will work. One semester they will study. So this is for undergraduates, not graduate students. So they will join in September. A lot of them will be there for that one semester, and then in January they're out there doing engineering jobs. Then they come back and so on. So it takes about 5 years. But the good news is when they graduate, our students already have 2 years work experience, so that they gives them a lot of edge when they go into the marketplace. And many of our students get hired by their previous employers. So it's a very attractive system, and Waterloo is known worldwide for this large co-op program. So my lab is called the Structural Dynamics Identification and Control Lab. So these are some of my students taken maybe about a year ago, I think. So some of them have graduated, new ones are coming in. But essentially, as the name goes, we work in the areas of structural dynamics, identification, and control, which are all sort of interdisciplinary areas now that I'm going to just briefly touch upon. So that brings to civil engineering today, right? So when you're a civil engineering student right now, your curriculum may not have changed a lot compared to what I was studying. We study strength of materials, we study highway engineering, we study foundation engineering, we study geotechnical engineering. So these are all very subject civil engineering subjects like water resources engineering. But what is happening outside the curriculum is civil engineering is sort of becoming very interdisciplinary, right? So I'm just giving you some examples where a lot of the applications right now in civil engineering are at the intersection of computer science, mechanical, electrical, because you cannot look at a structure and say, oh, it is just a civil structure, because now you are instrumenting the structures with sensors. You are trying to understand how they behave, when there's an earthquake, when there's wind. So you are sort of probing these structures, and they have almost become like a living organisms. So I'll give you some examples here. On the top right, that's the Golden Gate Bridge in San Francisco, and that's in the northern part of California. This is a very heavily studied structure, and people have, and I'm sure they still are, putting a lot of sensors to understand how they behave during earthquakes, because in that part of California, as with the southern part of California, earthquakes is a big problem. So they're trying to understand, just because you build, you cannot forget the structure, right? So you have to understand how it's behaving, and they're sort of putting these sensors and seeing how they behave along, how the structure is behaving when there is very small tremors which occur very regularly, so that they can predict how the structure is going to behave for larger earthquakes. At the bottom left, I show you MyoVision. So this is a company actually in Waterloo, in Kitchener, which is the adjacent city. This was started by some of our own students. What this company does is they make this intelligent traffic cameras. So, they can count automatically how many people are crossing in a road, how many vehicles are passing. So all these are video analytics. So they are taking all this data and trying to understand, how do you better manage highway intersections, right? How do you do traffic signaling? So this is very different from what you're reading in your highway engineering or transportation engineering course, where you're looking at, highway design or things like that. But now a lot of the civil engineering is sort of evolving in new directions, where you're applying sensors, you're trying to get the same information. So this sort of brings that interdisciplinarity thing that I'm talking about. And on the right, I'm showing you a seagoing vessel where they're building what are called digital twins. What they're doing is they're creating these finite element models, which are almost live. That means they are getting updated as your ship is getting more and more degraded due to corrosion. These models are getting sort of updated in real time. Again, this requires a lot of computational power, parallel processing. A lot of it is computer science. So these are all the things I want to give you examples of what civil engineering is, what's happening in civil engineering outside your traditional applications today. So since my talk is about bridge, I'll just tell you what we are doing in bridges. So when you look at bridges, there's a bridge in near Toronto. This is called the Gardner Expressway. And you can see large parts of this bridge are deteriorated. At least visually, they look very degraded, even though thankfully, structurally, they all seem to be working okay. But you want to be able to inspect them regularly, right? At least in North America, and I'm sure this is the case in India too, that bridges have to be inspected regularly.
Yes.
And what people do nowadays is, if you look at the top right of your screen, they use all this expensive equipment, send people underneath these bridges to visually look at them, or take a hammer, tap the decks to see if there is any voids. They drag chains on the deck to see if there is any damage, or sometimes access becomes very difficult. Let us say there's water under a bridge. An inspector just stands out on the shore wherever he or she can get some access and looks at it through binoculars. Clearly, what I'm trying to say here is it's very difficult to do these things manually. So what we started doing is, here's another example, how difficult it is to inspect bridges. These access is so difficult. Sometimes people have to put on these very elaborate safety harnesses. You have to sort of suspend yourself. Clearly, there should be a better way to do these inspections. And this is where a lot of some of my work has been in the last few years, where people have sort of used robots to do this inspection. So why do you want to send people into these risky situations? We can send a little drone, equipped with cameras, and so that you can take a lot of pictures. And just having pictures is not enough. You can then use those pictures, you should be able to use them effectively. For example, can we use any artificial intelligence like machine learning type algorithms to detect defects? And on the right is one of my students on the same Bridge Gardner Expressway. We are building these robots that have got similar sensors, right? So they got cameras, they got lidars, they got all sorts of really sophisticated sensors that you could just sort of take them under the bridge, and it can sort of create a digital map of your structure, so that then you can sort of quantify defects. For example, how much of this concrete has area is lost, and how does this relate to the strength deterioration in concrete bridge and things like that. Here's the robot that we built. So this is basically built in my lab, where it's got a whole bunch of sensors. You can take this robot to a bridge, and you can see all the sensors on them. You got lidars, you got GPS, you got cameras, you got infrared cameras. So we are sort of building a lot of these things. Now remember, when I'm showing you these things, this comes back to that whole interdisciplinary thing of it. It's no longer just civil engineering. This is robotics. That means you have to understand electrical engineering, you have to do computer science, because a lot of the algorithms that are there to build these maps, I'll show them what maps look like, are based on computer science and things like that. So civil engineering is becoming, at least on the research side and also application side, is becoming very, very interdisciplinary. Now you have to graduate not just as a civil engineer, but having this very broad understanding of how sensors work and things like that. So here's another map. I showed you a map, right? So what happens is you can take these robots inside here. I'm showing you on the right a parking garage. You can just go inside and create this very detailed map of a structure. Map means think of these every point as XYZ coordinates, right? So you have scale, and you have, I can tell you from this map how tall this column is. I can tell you how large this window is and how large these pillars are. And if there are defects, I can say how large these defects are and what kind of defects there are. Here's some examples of some bridges we have mapped. So on the left, I'm showing you a regular bridge, like a picture of a bridge, and then overlaid on them a lidar map. What each point tells you is the XYZ coordinate. Now I can measure things, right? So in an image, if I just give you a photograph, you cannot measure, but on these lidar maps, I can measure. And by having this ability to measure, we're able to sort of detect all these defects. Like here, I'm showing you delaminations in concrete. Delaminations are these subsurface voids that occur in concrete. And because of the thermal gradients, you are able to sort of detect them in the infrared images. So here I'm showing you how we have used our robots to detect and quantify. It's not enough to say, hey, there's a delamination. We want to be able to quantify them, like how large is the delamination, or how long are these cracks, and how wide are these cracks in concrete, so that once I have this information, I can now go into finite element models, and I can input these quantities, and I can see how much my bridge has deteriorated, or how should I inspect it, and so on. So it allows me a lot of other functionality and capabilities that I otherwise will not have just by doing visual inspection. So that's sort of like a very broad overview of what we are doing in my lab. But I think, as I said, I'm more than happy to sort of use the time to talk and answer, try and answer your questions, right? I think that's going to be very useful as well. Of course, I'm more than happy to talk to you about my research as well. But I think any questions you have, I'm more than happy to answer, okay? Thank you.
Okay, sir.
Okay, actually, I was wondering this. You have done
Sir,
a great job. Oh, Aditya, you want to continue? Yeah, continue.
no, sir, you can continue, sir. It's better.
Okay. Hello, Professor. Actually, you have done a great job, because here also, what happened, we got one consultancy project. Initially, we were talking about this project, but what we found that the difficulty is that how we can access that different part of the bridge. At the end, it did not come to us, but initially we thought of that we will try to go and inspect it, but again, we see the difficulties. Okay, so what I feel that you have done a great job on that sensor, all the things, robot. So suppose anybody want to use your robot, okay, or the product, so they buy it, or
No, so as I said, right, we on a research, a lot of these platforms, the individual components you can buy, right? You can buy a
Okay,
camera, you can buy the robot, that just the platform itself, it's available
okay,
commercially actually through a University of Waterloo startup company. But
okay.
a lot of this work, all this is system integration, right? So this is where a lot of custom integration has to come. All the maps that we create, there
Yes.
are some products you can buy, but it will not do what we want to do. So a lot of it you
Okay.
have to do it yourself, and that comes back
Yourself.
to the first point I made: is civil engineering students now have to know computer science and have to know electrical
And yes.
engineering, because you can buy this individual to buy a camera. You don't need to know how a camera works, but to
Mm-hmm.
take these cameras and integrate them into a robot so that it can deliver the application that you're looking for, you need to understand all of the things, how all of these parts fit together, right? So
Yes.
the way I'm saying that is, if you want to just use your iPhone or cell phone, you don't need to understand how a cell phone works. You just need to know how the applications are
Mm-hmm.
controlled. But if you want to change some application, or you want to put some new application on your iPhone or in your Android phone, you have to understand software. You have to understand, at least on the software level, how these things are built. So you work with APIs and things like that. Similarly, we work with a lot of these APIs, and we work with a lot of we have to sometimes build our own hardware. Short answer is, drones with cameras you can buy, right? So
Okay.
and you
Yes.
can use technologies that are off the shelf, but the ground vehicles that we are building are
Yes.
very
Yes.
specialized, and we had to build everything. A lot of the system integration is done by ourselves.
Okay. So I was asking another questions. You see that just you say that in India we are still we're dealing with the basic courses in the civil engineering, and I also feel that coursework should be updated as per the modern demand. So suppose any civil engineering student want to work in this type of things, what the special course they need to attend? Suppose they want to build some inspection robot or something, just you are working on this field, okay, it's generalized field. So what are the coursework you recommend that, yeah, India should introduce here,
So
so
I
that
don't think, maybe I wasn't clear. So I don't think the curriculum, we have to change the core curriculum, right? I mean, we are still
yes,
producing, in the business of producing good civil engineers. Of course, we
yes,
need to update with newer methods, but that can be
yes,
done. Like if you have a new concrete code, you have to sort of update it. You have new, you don't want to be teaching, slope deflection method for a whole semester anymore. You can teach, matrix analysis now, because a lot of it, or finite element analysis. So you have to update them. But the larger point is, as civil engineering is moving towards this interdisciplinary applications, yeah, students should be given more opportunities to learn outside their courses. For example,
yes,
right? Let us say you have a colleague in mechanical or in electrical who has a lab. I think civil engineering students should say, oh, you know what? I want to go work in their lab for, I want to sort of get engaged, so that I understand how, a little device like a Raspberry Pi is built, right? So many civil engineering students may not even know what a Raspberry Pi is, but Raspberry Pi is a small computer, with a small form factor, so you can do a lot of high level programming there. So I think the key thing is, I think, either integrate, like for example, if you have projects, like you're doing a fourth year project. I know Rishabh, one of your students, was doing work with Raspberry Pi or Arduino, I forgot what it was. But basically, encourage projects in your fourth year and in your third year that allow them not to do robotics, because that's a lot of undertaking. A lot of my students come here, spend 1 or 2 years just learning a lot of the basics. But simple things like Raspberry Pi, Arduino programming, also programming heavy concepts, like encourage them to do things more on these kind of things, rather than build a lot of beams and test them. Like a lot of these student projects tend to be, I'm going to take a lot of concrete cylinders and make some small change in it and test 100 of them or 50 of them, right? So those are important, but you should also sort of encourage projects that are like, oh, can I put a sensor now inside this concrete specimen, and instead of just looking at load versus strain, I can look at oh, how something is changing internally, like can I put a crack sensor there? So then I have to do some programming, you see. So how we deliver some of the existing courses can be modified, I think.
yes. Actually, that's the thing I was asking you. Okay, so yes, okay, I got it. No, initially, I thought that can you introduce some interdisciplinary course so that one civil engineering student can attend particular course and and so
At
that he
MTech
can.
level, yeah, if you have MTech students, I would
Yeah,
say
we
that
have, we have, we
you
have,
can.
we have
At an
intake. Yeah.
undergraduate level, I think you have to. I always find that students, if you expose them to these things, all you have to do is open the door a little bit and show that, oh, there's a whole world out there, right? And then a lot of students are so bright that they will just blow through the door and just blow your mind away. That's what I find, because you just have to kindle that curiosity. Once they
Yeah.
become curious, oh, what is this Raspberry Pi? What can I do with it? And then you will be surprised how many creative ideas will come from
Yes.
the students themselves. You just don't have, you can just step back. They have so many resources now available. Courses are good, like theory, right? You have to, like, but many of these things at an undergraduate level, you don't require to understand a lot of theory. You just need to understand how to program, how to make things work, right? So that's enough at an undergraduate level.
Okay. Okay. Thank you. Aditya, you now continue with your quiz.
Ye- yes, sir. So I would like to ask you that due to the global pandemic, most of the learning process has been affected and most of it is going through in online mode. Like, how is it affecting the students' practical experience about the subject, and how is it going to affect the field of research?
Yeah, I think so. I think what I would say is with the current situation with COVID, a lot of the instruction has gone online, and it is affecting the quality of a lot of courses. I mean, it is not just in India or country specific. Even here, anecdotally, we don't have all the data yet, formal data yet, but at least we have a good idea that students are not happy with the quality of online delivery they're getting. It's one thing to just stay in the class and interact with the students, but it is a completely different thing where you have to record your lecture. So there's that. Now, your other question was the long-term implications for undergraduate teaching and research. I personally think that it's hard to say what the long-term implications of this is going to be, because we do not know when this thing is going to end and how this is going to end, right? How we are going to go back to normal and what that normal is going to look like, and how long will it take for us to get back to normal. If the current situation exists, then you can expect that the quality is not going to be great for undergraduate education, right? So I'm hoping, I'm just being an optimist here, that this is in the medium term. Maybe all this will get sorted off in 1 or 2 years so that we can go back to our original successful models of delivery. For research, the only parts of research that are getting affected the most is in two areas, actually, from our point of view. One is experimental work. So a lot of our students are not able to get back into their labs, which is changing now. At least in Canada, our students are getting back into the lab this month and slowly getting back into the labs next month. So I think we've lost about 3 to 4 months of productivity in the lab. But people who have worked in computational work or programming and things like that, which is where their work is portable, I don't think it has affected that much. So all that work has happened. The other aspect where I think it has also affected is a lot of, unlike India, or maybe in India this is also true. Here, some of the funding is actually provided. A portion of the funding is provided by private companies. We call them in, and then the government matches some of these private company funding. So as a result of COVID, many of the private companies are losing their business streams. So because they lost a little bit of business, they are sort of pulling back on their commitments. They say, hey, we said we were going to give you money, but now our situation is not good. So sorry, we can't give you this year's money, right? As a result, some of this funding is getting disrupted. So there are implications, but I'm thinking much of this impact is going to be short term and medium term. Medium means 1 or 2 years, but I'm hoping that a lot of these things are going to come back to at least where things were before COVID happened.
Mr. Sagar Tripathi has asked, whether the mobile robotics used for bridge inspection in your research can be used as evaluating the building response. Can the same robot be used for both the purposes? And is there some need for software or algorithm changes?
Right. So I think one question, one I would say look at it is like let us look at the application and then see what technology is the best suited for that application, right? So why do we have a robot? Robot, the main advantage of the robot is mobility, right? I think you use them in applications where you want to move around a lot. And moving, like for example, we are using these robots in nuclear environments. We are using it in environments where access is difficult, and it is possible for us to use these platforms like drones or ground robots. When you talk about structural deformations, if for example, if you want to look at post-hazard earthquake scenario, like let us say you have an area that is during earthquakes has been damaged a lot and access to people is very difficult, then you can send these kind of mobile vehicles to sort of survey the area, right? And yes, you can get a lot of quantitative information out of it. But if you're looking at bridge vibrations or bridge displacement, I would use stationary systems which are actually instrumented directly on the bridge, or some other remote capture stationary systems. I don't know if mobility is something you would need there, because mobility, remember, adds a lot of complexity. And you don't want your problem to make your problem very complex when you can get away by using the simpler thing. So I always say, if you have a nail, the best tool to use for the nail is a hammer, right? Not a jackhammer or not a very big concrete block, right? So you have to sort of look at your application and say, what is the easiest way and the best way to measure? And if you're looking at structural vibrations, I would use stationary systems, not mobile systems, although cameras themselves can be used for a lot of displacements, and that's perfectly fine. You can put them on tripods and things like that. But a robotic application itself is very complicated. Unless it is absolutely necessary, then I don't know whether you're going to gain any advantage. So I'm reading a question
How
here.
feasible would it be to implement? So, going again, one of our audiences, Saurabh Sahu, has a question. How feasible would it be to implement the technologies in India, and their cost effectiveness and the efficiency in Indian terrains?
Yeah, it's a good question. Actually, in India, there's a lot of potential to use. I would say for bridge inspections, a lot of potential to use drones, and I know people are using it. Drone-mounted cameras, for example, especially in Indian railway bridges, there is a difficulty in inspecting a lot of these bridges, and our loads keep going up because of a lot of reasons. And I feel that there is a lot of opportunity to use things like drones to do it. But in India also, we have to be a little bit more contextual. The problem is also that a lot of the infrastructure in India, we have to evaluate them through more traditional means too. Like, for example, is it better for us to, if things have far surpassed their end of life, should we be looking at investments, capital investments, and things like that? Technology can solve small part of the problem. It cannot solve the entire problem we have for infrastructure. So I would say that, for certain inspection things, yes, you can use a lot of technology like drones or even ground robots or any other type of sensors. But to solve in general, for Indian climate, where we have infrastructure problems that are at a different magnitude and at a different scale, we have to also look at more holistic way to address them, like investment, better maintenance, better modeling, better capacity estimation. So you also have to do a lot of traditional civil engineering type approaches in addition to just applying technology, right? Like I always like to say this, in India, when I was growing up, we never had a landline for a long time. Wait list to get a landline, a telephone landline, was 10 years, 12 years. And then cell phones happened. So people simply ignored landlines and everybody leapfrogged, and technology helped them to leapfrog from no phone to a cell phone, right? But you cannot do that for infrastructure. In India, you cannot leapfrog what you have and just use technology to sort of go to the other side. You have to go through your regular replacement, improve the quality of infrastructure, make sure that the loads you are putting are correct, construction quality, construction, project management, all of these things also have to happen in India. So what is applied in developed countries, you cannot simply take that and feel like it's going to solve all of our problems. It will solve some of our problems, not a majority of our problems.
Another question from the audience. Abhijit Satpathy wants to ask, in India, we need to implement this co-work culture, 1 year study and 1 year implementation. Will this help us to understand and innovate the concepts in our way?
I'm very happy you asked this question, because I think I really think that in India, more than anywhere else in the world, cooperative education models are very important. I think many programs in India don't produce engineers who have worked even one day before they got their engineering degree. And I never worked one day until I got my engineering degree. So what I feel in India we need to think about is there's a huge demand. There's an industry demand, and there is also a need to train our students to adopt this kind of work. Let me put it this way. I've looked at Waterloo model. Before I joined Waterloo in 2006, I didn't know what a co-op education is. But after I've joined here and I've looked at what our undergraduates are in their first year, and when they're graduating in their fifth year, it's a very big difference in their attitude, in their maturity, and everything. I think what I find will give you, if you have this kind of a model where you can do 1 year you have to work, or you can even adopt the models like we have, right? It really depends on how you want to deliver. It's besides the question. The main thing that something introducing work terms or into your undergraduate curriculum is going to do two things. One is relation between what you're learning in your class and what you are applying in real life, right? So that link will become more firmly established. The other thing is it also give you a sense of pride, because a lot of civil engineers, for example, will feel like, oh, I am in civil because I did not get electrical, right? So this is kind of an attitude. But what I find a lot of times is when civil engineers actually go and work for a company that does design, many of them will come away thinking, oh, what I'm doing is so important. This bridge I'm help designing, or this whatever structure that I'm building, or water resource project that I'm working on, or some geotechnical foundation design that I'm doing. These are very, very important, and it will inculcate a sense of pride that you will understand what a civil engineer can do and not what you're taught in your textbooks, right? I think I really a big proponent of having this kind of internships, make them even mandatory, and provide. It's not just enough just to have a rule, right? I think there should be a whole ecosystem. We have over 7,000 companies. I forgot how many companies come to Waterloo to recruit. Right? It's not simply enough to say, oh, all our students have to go to work. Where are they going to find work? So you can. I'll give you, I think, one of the examples. I think Professor Mandal is asking, what is an example of a co-work? Okay, I'll give you an example. In civil engineering, we have students who go work for companies like GHD or ACOM. These are big construction companies, and or design companies. Sometimes they go to work companies like Arup, which is a very large design company. So they go, let us say, they in civil engineering, for example, they come in September, and then first semester they're studying, and then in the second semester they're going to work for one of these companies. So there are over 7,000 companies that come to recruit from Waterloo. So you can name any company, and chances are there's a Waterloo student who has done an internship. In fact, I'll give you one example. My own PhD students right now are doing internships with Facebook and Amazon, and they're civil engineers because they're doing a lot of robotics work, right? So the question is, I think I've just answered one of the questions that came here, but to give you an example, but to end this question, yes, it's very important. In India, it is more than just important. I think it's necessary. And to make this happen, the universities like NIT have to bring a lot of these companies, those Tatas, those L&Ts, those companies that are there in India, and bring them to campus and sort of facilitate this interaction where they're hiring intern students, maybe during the summer or however you're structured. Long answer, but I think it's a very important one for Indian context.
Moving on to the next question, we have from Subhajyoti Jena. He says, is it possible to pursue MS or PhD in the field for a civil engineer with little to zero knowledge during undergraduate level? And how difficult will it be? And the challenges faced during the initial stages?
Yeah, I think it will be challenging, and MS is going to be difficult because MS is generally depends on where you go. They are one way from 1 year to 2 years, so you can get some basic understanding of these things. But a lot of the things like very interdisciplinary research is generally done at a PhD level because you're almost at the stage going and learning a lot of new classes. Like you have to go to computer science to take a software programming course. You have to go to electrical engineering to take signal processing, control systems. So you have to take all of these courses. So it is possible. When I did my undergraduate, I was a civil engineer, but when I did my PhD, it was in control systems. So, and my students too, they join, a lot of them are civil engineers who join, but when they finish, they're working for companies like NVIDIA and Facebook, doing not software, but they're working on robotics, right? So they are mingling with people who are electrical engineers, they're mingling with people who are pure computer science people. So it is possible. And you have to work harder because you have a higher barrier to overcome. But what in the end will happen is because your domain expertise, because you're a civil engineer and you understand your problems better, you can actually come much further ahead because you are going to be able to develop these solutions that are much more tailored to your problems. That, for example, a computer science student will not be able to tell you how to design a better bridge inspection system, right? So that's where I think we have an advantage. But the short answer is yes, it is possible, more for a PhD rather than an MS, and it will be very difficult, but I think the rewards are also going to be much higher.
We have from Vaibhav Singh, what is the role of civil engineering in the field of smart infrastructure, smart city?
Yeah, I mean, as I said, smart city has been, or smart infrastructure has been thrown, dandied about for a while now. What it really means is you're building intelligence into non-living things, right? Like buildings and highways, and where you are embedding, like in a very simple sense, you are embedding sensors into objects or into structures or into signals, intersections, right? So civil engineering, a civil engineer is at the core of these things. For example, I showed you Myovision example where they're measuring all the traffic volumes with cameras. Yes, you can get a computer science and an electrical engineer to build that camera system, but a civil engineer is the only one who will be able to take that information and be able to usefully apply it to better design that intersection, right? So at what times, what should be the signal timing, how many cars should be managed, right? Managing that intersection is still a civil engineer. Same thing, you can have an electrical engineer build a sensor, but if it's on a bridge or a building, it's a civil engineer who has to understand how to use that information, because they're not going to understand how bridges behave or buildings behave or a dam behaves. So you are at the center of using it. So without a civil engineer, there's no smart city or infrastructure, in my opinion, because all you have is sensors that are measuring something.
Moving on to the next question. Shubham, can you please display the question? DR Mahapatra has a question. He wants to ask whether you're using the same traditional software for mapping the structures.
Um, I so I think okay. So let me try and understand what the question is. I think traditional software. There is no traditional software for these things, right? So you have to write everything. A lot of it is either open source or you have to, which even then you have to integrate it yourself. So the short answer is for some parts of it there are open source tools, but for a large majority of the work that I've shown you, my students basically wrote much of the code, even though individual functions might be available. Just like in MATLAB or something, if you have used, you can call a function to multiply two matrices. That's available. But how you put together that whole program, your program is more about just multiplying two matrices, right? So you have to do all the other things. So all that has been written. So short answer is there's no traditional software for the things that we are doing. There are components that you can get in open source community, and some of these components are also available for purchase, but they're all not in a form that we can use for the application we need. So we have to take them and we have to engineer them, and we have to come up with our own ways to integrate them. So no, I mean, parts of it is open source, but part of it is a lot of it is just my own students writing these things and developing a lot of these mapping algorithms and applying them and processing them and so on.
Next is a question from Havisha Kotla. She asks, so what qualities do you look for while hiring students?
Yeah, I think so. Okay, so let me give you some examples, right? I think now masters, like I generally don't hire students at a master's level directly because for the kind of problems that I told you that it takes a long time to learn. So the qualities, one of the major qualities I look for is academic excellence, right? So you have to be really at the top of your class. May not be one, but you have to be, the top five, or and you should get recommendations that are very strong. But also, I'll tell you one thing, right? On average, faculty like me, for example, all around the world, I would say on average, one or two emails every day of the year, nearly every day of the year. So even just me, I might have 400 or 500 emails from people who ask me if they can come do a PhD with me, right? So I only have one position or two positions a year that I hire from India, because I also hire locally from Canada. And this is the same thing across most universities, good universities, which are competitive to get in. So you have to have the main qualities, I would say, is be academically extremely strong, so that you say, oh, that I've shown that I can excel, and show that you do things that are different, right? Like, for example, if you're applying to me and you say, hey, Sriram, I want to work with you in this area, the first thing I'm asking is, why do you want to work with me? What can you show in your resume that tells me that you have an aptitude for this, right? So I do things on sensors, instrumentation. What have you done? What have you done in your undergraduate that is outside your curriculum that shows me that you're interested in it, right? So I want to see that. I want to see something different that you have done. And I would say most people would like to see that. That the candidate has done something different other than being at the top of the class, because most students who apply to me or to my colleagues are really very strong academically, but most of them don't get admissions if you apply. So you have to put in work. Like, you have to think about, okay, I want to do a PhD, or I want to do something, and I want to work with this person. So identify early. Make sure you're at the top of the class or you're excelling academically, but at the same time, do some undergraduate project, maybe your fourth year project. Do something that to show that you have actually an aptitude in what I do. Because I'm not going to hire somebody who says, oh, I'm a first rank student in IIT, whatever, and my fourth year project was, I designed reinforced concrete beams to, this. I say, look, it's not for me. Like, I don't do that. So it doesn't matter. you have not shown any aptitude yet. So I would rather hire somebody who's a fifth rank or a third rank person in the class, but has actually done a Raspberry Pi project and said, hey, for my fourth year, I did a Raspberry Pi project. And I like the kind of you're doing because I also like instrumentation. I also like to be interdisciplinary. So that's how I would say start thinking.
Performed using the robot to determine the dynamic response or the seismic performance of the bridge?
Seismic performance of a bridge. Okay, dynamic response and seismic performance are a little bit different. Okay, so I'll maybe answer this a little differently. The short answer is perhaps it is possible. For seismic performance, you could probably map the entire bridge, convert that into a finite element model, and then from the finite element model, you can sort of run your analysis, right? It's possible. For dynamic response, I would ask the question, why would you want to do that? Why would you want to have such a complicated robotic system to do a dynamic response when all I need is accelerometers that I can put on the bridge, and I'm able to collect the data and get the same answer? So the short answer for that is it's perhaps possible to get dynamic response from perhaps not with the robot. You can just use the cameras to get them. But I will always ask the question, there are much easier ways to get a dynamic response, like you can put accelerometers on them. And nowadays you have a cell phone. You can just put your cell phone on a bridge, and you can see that it picks up a lot of the major modes of vibration. So I would say it may be possible, but I wouldn't do it unless there's an absolute necessity to do it. Seismic performance, sure, right? You can map a bridge, map it to a finite element model, and then from there you can sort of look at what defects there are on the bridge and model them and things like that. Yeah, seismic performance perhaps. Dynamic response, I would not use it unless there's a good reason for it. Yeah, I guess I can just read out this question because I'm seeing it. This is from Rishabh. Do you believe that a complete revamp of the undergrad? Do you believe that a complete revamp of the undergrad curriculum, especially in India, is required to make a comprehensive graduate instead of just relying on? It is very difficult to do a complete revamp of the undergrad curriculum, right? I don't even think it is needed. I think what we should do is because remember, civil engineering curriculum is supposed to produce civil engineers, right? We don't have a civil engineering curriculum that is going to produce a person who knows computer science, electrical, mechanical, and civil. So that's not a curriculum. There is a curriculum for it. That's called systems design. So if you want to start at the undergraduate level, you can do something like systems design. But what I would say is what we need in India is not a revamp of the curriculum. Maybe updating materials regularly is needed, right? You have to update, your matrix analysis is not talking about slope deflection method and writing exams and these things, but it's involving programming, it's involving all those things. So update is required. But I think what we sorely need, in addition to updating our curriculum, is creating opportunities like in projects where students can sort of expand their horizons like you have done, right? So you are doing some sensors for your fourth year project, which attracted me when you email me. So that sort of thing is important, I think, to create opportunities where you can sort of spread your wings and learn other areas like programming, like Raspberry Pi programming or Arduino or microcontrollers, and just a curiosity, show opportunities in courses. If you're doing a concrete materials course, maybe do a project, and those kind of things are important. A revamp of the curriculum is not needed because we don't want to become an electrical engineer. We just want to understand enough about electrical engineering so that we can solve our problems in civil engineering. So, with current computational power, can we capture the entire response of complex structural systems under extreme loading conditions by integrating diverse range of? Oh yeah, I would say that, I mean, a lot of it is, I don't know what complex is complex, but I think the arguments we had 10 years ago of not having computational power, that we cannot do these things, is no longer valid. Now I would say that it still has limitations. I mean, there's not unlimited compute, but nowadays you can do a lot of things that are not limited by the complexity of the system. It's just you just have to figure out how to program it better, right? So if you are doing, say, for example, the same thing over and over and again, and there are no dependencies, can you write your software program so that you can use a GPU, for example, right, instead of a CPU? Can you parallelize your code? Can you write your programs more effectively? Right? I think you have to be creative. It just say that, okay, I am the point I'm trying to make here is, there is enough compute, but I think the limitation right now I see a lot of times is people are just not writing programs properly to use them, and they complain that, oh, I don't have enough compute. But I'll say, well, you have not really parallelized your code when you could. You're not doing this effectively. You don't have to run this 10,000 times when you have to run it only 100 times. So those kind of things, some algorithmic and programming changes can help alleviate the issue. So the short answer is yes, I think we have more than enough compute. But the long answer is, again, it's application dependent, but also it will involve us to rethink how we write our code. And again, comes back to why civil engineers have to think. I'll learn a little bit more about computer science, because we can bring a lot of ideas of writing proper software programs, not just the kind of programs that we are used to writing in our curriculum.
I have one question. Can you hear me?
Yeah, I can.
Oh, so you just talk about that breeze model in FE. Okay, so suppose we want to perform dynamic analysis in breeze. So it will be very difficult, and it will take high compression time for the FE model in that, suppose ANSYS or Abacus if you used. So which software you are using, or you are suggesting that students will learn, or at undergraduate level? Because see, if you want to get the dynamic response using FE models, the huge matrix size, it will take a lot of time.
Correct.
Okay, so
and yes,
you are
I think
suggesting for having a server for that, or you can change the software instead of find element or Midas. We have actually next week we have one software training program on the Midas bridge engineering. So they used to do modeling on the bridge, and basically it's easy for that bridge modeling, because they already have some cross section. You just extrude it and do the analysis. Okay, so but that is not again find relevant software. That matrix method probably they are using. So what I'm asking, that if anybody want to go for the find relevant analysis, then which software they should use, or server, or whether they need the server or not.
So it really depends on application. So let me take a step back, right? So the way I look at it is, okay, so you have a large FE model. And if you're interested in just the global modes of your structure, let us say if you're only interested in the first mode of the structure, then you can limit within your algorithms. In most programs like Abacus, ANSYS, any of these finite element softwares like SAP 2000 now has also got these things. There are many, many settings that you can use, right? So you can say that, okay, limit my modes to just the first mode, right? Then you can use what is called dimensionality reduction. A lot of these things are use reduction techniques, right? For example, finite element models can be reduced to much smaller models, right? So you can create within these programs, there are so many tools available that will reduce your complexity. I find a lot of students, what they do is they create a model that is extremely rich, like million nodes, and then they hit 20 modes and they click, okay, do me modal analysis for this. And I go, why? Of course, if you want to do modal analysis for such a large system,
Yeah.
you need to have large servers, like you need to have large CPUs, right? So in my lab, we have a server that my students use for mostly soil structure interaction sort of problems, right? Because soil becomes a little bit, because it's non-linear models and things like that. But if you're doing things like linear analysis, then it's a lot simpler. Now, if you're doing non-linear analysis, like if you're putting geometric nonlinearities and material nonlinearities, and you want to look at, earthquakes, then you have to expand your compute power. I think things like Abacus, ANSYS, all of them are able to do pretty much nowadays the same thing, because they've all sort of competed over the years, and they've all sort of reached some level of equality that way.
Yeah.
So as long as you understand that whether you're doing a linear analysis or a nonlinear analysis, whether you're doing a modal analysis or you're doing a full time history analysis, the computational requirements are extremely different. To answer your question, I don't know whether Abacus or ANSYS is better or some other software is better. I really don't think for a lot of the work we do that is that important. But maybe it is that if you're doing concrete mechanics, there might be some software programs that have some inbuilt models for concrete that maybe, things like other programs may not have. But I am not an expert in material mechanics and things like that. But for dynamic analysis, I have not found any problem with any of these things. And make sure, as long as you know what you want out of it, and you are utilizing all the options in your compute module, or in your algorithm module, where you're saying, okay, limit the number of iterations, what algorithms, numerical algorithms you're using for convergence, and what your convergence criteria are. So if you understand those things and set them properly, you can get away by using less compute and be able to solve the same problem.
Okay. Okay, Aditya. Next, do you have any questions?
Like now, I would like to take up the last question from Aditya Kar.
Yeah, okay. So he's saying, how can one see civil engineering after 10 to 20 years? Is it equipped with the automation part or still conventional type? As I said, it's a continuum, right? It's a continuum where things are evolving. Your bridge is still going to look like a bridge, right? You cannot, I don't think people are going to be transported from one end of the valley, one end of the hill, one part of the hill to the other part of the hill in an airplane without a bridge. So bridges are still going to be around. Roads are still going to be around. Automobiles in some form are going to be around. So the infrastructure part will be a constant, and how you design them and how you maintain, how do you design them and construct them. A lot of these processes might become more efficient and faster, but I think all the basics will not change. But I think where things are going to change in the next 10, 20 years is, as a civil engineer, we have to learn how to prolong the life of what we have. Make sure that what we have is safe. For example, if you have a railway bridge, you cannot simply say that, I'm going to put this railway bridge in and I'm going to worry about it once somebody complains or it starts to fail, right? We have to be more proactive. So where I think a lot of the things are going now is in inspection and maintenance. I think that's where you're going to see a lot of technology being used, either drones, robots, or sensors. All of these things are going to make their way into these maintenance and inspection part. The design parts are going to get more efficient. I've already seen a lot of people using machine learning, things like that in coming up with better designs and more rich variety of designs. But I think we have to, like, civil engineer has to change, just like, for example, electrical engineers changed from an analog world to a digital world pretty easily. They went from an analog when, 40, 50 years ago, all they were learning is those analog circuits. And now the analog part in their curriculum is very small. Most of it is all digital. So same thing, I think in civil engineering, what's going to happen is you're going to see a lot of projects that are very interdisciplinary. And you're still going to have strength of materials, but you're not going to be spending 3 years with 5 courses in mechanics of materials and strength of materials. Maybe a lot of that is going to be condensed into something that is in a couple of courses, 2 or 3 courses, and then all of a sudden now you're going to be taught smart infrastructure, like how basics of electrical engineering, which is actually kind of expanded into digital area, right? So those are the kind of things I think are going to happen in the next 10, 20 years. We still cannot become roboticists, right? Civil engineers are civil engineers. We cannot be designing airplanes and drones. So I think that part is best left to them. What we have to do is we have to at least have enough domain understanding how to effectively use it in our application. So I would say it's in a continuum. Things are going to evolve, and we are going to go more and more into the digital world. I'm not be surprised if you start getting courses in some undergraduate curriculum, especially in the upper years, where basics of Internet of Things or basics of sensors and things like that. So yeah, so that's sort of like my short answer.
Most of the major questions have been covered. So I would like Shubham to proceed with the vote of thanks.
Hello everyone, myself Subham Das, a third year undergraduate from the Department of Civil Engineering of NIT Rourkela. I am the current technical head of IC UK NITR chapter and one of the organizing secretaries for the event Civinar. Let me just start by saying how grateful we are towards Professor Sriram Narasimhan for taking his precious time and such effort to help us and educate us. Having delivered his webinar on automation in bridge inspection, he not only fueled our knowledge but also motivated us in the field of science and engineering. Everything he taught us today, I am sure it will be invaluable to all of us in the future. And sir, we are all thankful to you for that. Now, I would like to thank Professor Subhajit Mandal, the faculty advisor of CEST Club, whose constant guiding presence has been and will be indispensable. I would also like to thank NITR and SEC for giving us this chance and such constant encouragements to do events like this, which will surely help us grow and develop. And of course, the webinar would not be complete without its lovely audience. Thus, I would like to thank you all for attending and making it a success. And last but not the least, I would like to thank the organizing team for this event who put tireless hours into making this event possible and seeing it through. Thank you all for turning up for the session. We hope all of you are keeping safe and doing well. We will be having more such interesting sessions in the upcoming days. So stay tuned.